There exists a simple relationship between integrals and infinite sums that we will use frequently in physics when we want to solve complicated problems. To show this relationship, we start by calculating the area underneath a function. In this case, the function is chosen as a straight line, and we want to calculate the area underneath this straight line between the values x1 and xn as shown in the graph. We can start by dividing this area into a rectangular area A and a triangular area B. The rectangular area A is just given by the width of the rectangle times its height, which is given by this expression. The area of the triangle is just given by a half times its base times its height, which is given by this expression. We can add these two individual areas together to get the total area, giving us this expression in terms of x. Now, there exists a simple relationship between the straight line equation and the area underneath it, bounded by the values x1 and xn. And this expression is just the definite integral of the straight line equation. If I calculate the definite integral of 2x plus 4 between x1 and xn, the expression that I get is exactly the same as the area underneath the straight line between x1 and xn that we have calculated above. Therefore, the definite integral of a function is just equals to an area underneath that function bounded by the two values at the beginning and the end of the definite integral. We could have calculated this area in a different way. We could start by dividing the area underneath the line between x1 and xn into a number of rectangles. Each rectangle is centered around a value of x, and the height of the rectangle is just given by the value of the function, 2x plus 4, at that value of x. If we divide this area into a number n of rectangles, we can approximate the area underneath the curve as just the sum of the areas of each individual rectangle with a width delta x. Our approximation becomes more accurate the smaller we make these rectangles. So we can write the total area underneath the curve exactly as the sum of the area of all these rectangles in the limit where the width of these rectangles is infinitesimally small. So we end up with an expression for the area underneath the straight line between x1 and xn as a sum of an infinite number of infinitesimally thin rectangles. However, this is just the same area that we have calculated on the previous slide. Therefore, we know the sum of an infinite number of infinitesimally thin rectangles is just equals to the definite integral of our function, in this case the straight line, evaluated between points x1 and xn.